Chabilski's star was discovered in the 1960s. Since then, astronomers have been intrigued by its unique chemical makeup. The star is suspected to contain ultra-rare elements, verging on the almost impossible. Using special equipment on the European Southern Observatory's telescope in Chile, researchers took readings of the star's magnetic field. They discovered that the star's rotation period, which is the time it takes to finish one revolution on its axis, stretches out over almost 200 years, which is super slow. Of course, there are even more bizarre objects called apstars. They're a chemically interesting category of stars that rotate extremely slowly, with one rotation taking up to 1,000 years. What makes these stars even more peculiar is a wide range of chemical elements astronomers detect when analyzing their stellar spectrums. But if we look at Chabilski's star, we'll see that it's both similar to and different from other apstars. It contains unusually low amounts of iron and nickel. Our Sun has 10 times more and incredibly high amounts of rare, heavy elements. Those might include strontium, cesium, and neodymium, as well as at least 2 undiscovered elements. They wouldn't occur through any natural processes we currently understand. There's a hypothesis that the presence of such heavy elements could be caused by a star's unseen companion, like a neutron star. Some people go as far as to say that such an incredible chemical makeup could be a sign of an alien technosignature. Any specialist will tell you that it's the strangest stellar spectrum they've ever observed. Some even claim that there are so many chemical indicator lines you can't immediately understand what you're looking at while observing the star's spectrum. Chabilski's star also contains high levels of radioactive elements that take a few thousand years to decay. And here's where another mystery lies. They should have long vanished from the star. After all, it's almost 1.5 billion years old. Scientists haven't managed to figure out the reason for the presence of these elements yet. Maybe it's the combination of the star's rare qualities. It spins very slowly, it's hot, and it has a strong magnetic field. This could raise to the surface atoms that would normally be mixed inside the star. There's another theory that explains the presence of these radioactive elements. They could be there as if they were themselves decayed forms of ultra-heavy elements that we haven't discovered yet. So far, no one has been able to prove this theory. Even the discovery of Chabilski's star's super slow rotation doesn't bring us closer to the answer. It's obvious that there's a lot to learn about the bizarre star, and who knows which secret it still has up its sleeve. Another not less mysterious star is called Tabby's star. It's a sun-like orb around 1,500 light-years away from Earth, sitting in Cygnus the Swan. Unlike our Sun, this star dims randomly by 5 to 22%, and it lasts for days at a time. The reason could be a giant planet passing in front of the star, but then the eclipses would be more regular and not so random. And if it was a Jupiter-sized planet, it would also need to block around 1% of the star's light, which would make it unique and unlike anything we know. After American astronomer Tabitha Boyajian discovered the star's massive and irregular fluctuations in 2015, further observations followed. They show that the overall magnitude of the star has been gradually dimming over the years. Some theories trying to explain this phenomenon are quite believable. For example, some scientists think that these brightness changes are intrinsic to the star. They could be caused by its magnetism or changes in heat flow in its interior. Other ideas are more daring, including some kinds of activity of an extraterrestrial civilization. One of the most plausible theories, though, is that the dimming is caused by the chunks of an orphaned exomoon. It could have been pulled away from its parent planet by gravitational interactions with Tabby's star. As the moon approached the star, it exploded, sending dust clouds into stellar orbit. These countless chunks of rock and dust are now moving between Tabby's star and Earth in a giant, clumpy cloud. It could indeed explain why we observe such irregular brightness variations. Usually, when astronomers spot a spiral-armed structure, it turns out to be a galaxy. But not in this case. SAO 206462, located 460 light-years away from our home planet, is a young star. It's surrounded by a circular disk of gas and clearly defined spiral arms. The bizarre star was spotted during an exoplanet search with the help of the Subaru telescope located in Hawaii. Instead of finding fully fledged planets around a young star, astronomers discovered planets that were still in formation. These baby planets are growing out of the disk of gas and dust surrounding the star. The disk extends out to around 80 astronomical units, which is twice the orbit of Pluto. At least 2 of these planets have stretched the disk into its extremely unusual spiral shape. A different planet is responsible for each arm. In our home galaxy, there's a giant star that is a real stellar wind machine. At the moment, this monster is just waiting to burst and send a wave of radiation and hot gas towards Earth. All because it's a Wolf-Rayet, a star which is at that precarious point before it goes supernova. Its core doesn't have any more helium left to burn. Instead, the star is forced to churn through much heavier elements, for example, oxygen. Unfortunately, it disrupts the careful balance between gravity and fusion, leading to the star shedding its layers. When the oxygen eventually runs out, the star will go supernova, but this time the show will be different. The thing is, WR104 is 1/2 of a binary pair, which means that 2 stars are feeding into each other, spinning up their stellar winds. It will continue until they start going incredibly fast. Is the potential explosion going to harm Earth? On the one hand, we're far away enough for even a directed supernova to not hurt our planet. At the same time, there's a threat of an extremely dangerous gamma-ray burst. Luckily for us, it takes a very specific and unlikely train of events for a Wolf-Rayet to produce a gamma-ray burst. Plus, even if it does, the star might be pointed far away enough for the danger to miss us. Anyway, astronomers are still watching the star, just in case. A star sitting in the constellation of Centaurus keeps a secret not many know about. At first glance, it looks like a dim white dwarf, but when astronomers analyzed it, it turns out to be incredibly dense. Take the mass of the Sun and cram it into something that is only 1/3 the diameter of Earth. This space wonder is also rather cool. Its core temperature is a mere 11,900 degrees Fahrenheit. For comparison, the Sun's core temperature is around 27 million degrees Fahrenheit. At such low temperatures, stars begin to vibrate. And then, scientists can use these vibrations to sneak a peek inside a star. And in the case with the star in question, which was later named Lucy, they discovered that its carbon core had crystallized. In other words, it formed a giant diamond 10 billion trillion carats in size. Since the discovery of Lucy, a few other crystallized stars have been spotted. Some of them have diamond hearts the size of our planet. The last bizarre star for today is called Vega, and it's squashed. The star's bulging waistline is caused by an extremely high spin rate. Vega rotates once every 12.5 hours. This pushes the material around its equator outward. It also leads to the phenomenon known as gravity darkening, when stellar material further from the center of the star experiences less gravity, which makes it cooler and darker. So when Vega faces Earth pole end on, it looks perfectly round. But the dark halo around its middle is a telltale sign of Vega's oblate shape.
Now, let's think for a moment. What if, instead of building spaceships to move across the stars, a super advanced civilization decided to turn their entire star system into a spaceship? That means a whole sun, the planets, all the asteroids, zooming through the galaxy together. That's what one philosopher, Clement Vidal, suggested in his recent space theory. There could be countless reasons why these extraterrestrials might decide to explore space. Maybe the star nearby is about to go supernova, blowing up and destroying everything nearby, including their home system. Or maybe they're searching for new resources somewhere in outer space or trying to spread life. But our galaxy has a minor problem. It's incredibly huge. So even if they move with the speed of light, getting from one star to another would take a gazillion years. Ooh. However, if we could just move our entire solar system, that would be convenient. We wouldn't have to change a thing or look for another star system and planet. How, though? Well, they'd use their own star as an engine. Literally, a stellar engine. All they'd need to do is push their star and everything orbiting it in a specific direction. You must cause the star to spit out material unevenly, creating a kind of thrust. It's like our rocket propulsion, but applied to entire stars. When more material ejects on one side of the star than the other, it acts like a rocket, slowly nudging the entire system along. Over time, they could steer it to wherever they want. Now, this isn't just some goofy idea, well, maybe, but many scientists have proposed different models for how a stellar engine could work, and how we humans could use it. The most famous one is called the Shikhatov thruster. Here, the idea is to use a giant reflective mirror to push a star gently in one direction by reflecting its sunlight. Other designs propose ejecting mass from the star itself. Of course, that'd be insanely hard for humans to pull off, but a super advanced civilization might just do it. And it might not be as hard as it sounds. There are already stars in the galaxy that move at incredible speeds. They're called hypervelocity stars. These stars are so fast they can escape the galaxy itself. Their story begins in the heart of the Milky Way. At the center of our galaxy lies a monster, a supermassive black hole with gravity so intense nothing can return from it. We even took a shot of it a while ago. Remember this one? It's called Sagittarius A star. We start with a pair of binary stars. They are similar in mass and orbit each other. Sometimes they stray too close to a black hole. When this happens, one star can get captured by the black hole, its fate sealed, while the other gets the wildest roller coaster ride of its life. It's like a crazy slingshot. It's hurled outward with unimaginable force. These exiled stars gain incredible speeds, like over 1,000,000 miles per hour, and become hypervelocity stars. Now, this doesn't happen that often. Maybe one hypervelocity star is flung from the galactic center every 100,000 years. And with over 100 billion stars in our Milky Way, finding them is worse than needles in a haystack. But even so, we managed to find about 1,000 such exiles in our galaxy. But anyway, could these superfast travelers be extraterrestrial starships? Maybe it's some wild move other civilizations decided to pull off, getting slingshot by a black hole so they could travel wherever they want at wild speeds. Now, most hypervelocity stars studied so far are single stars. But what about binary systems themselves? This binary system we mentioned would make this whole process of turning a star into a spaceship much easier. Another civilization could focus their efforts on one star in the pair. The interaction between the two stars could be used to fine-tune direction and spin, like a built-in steering wheel. It would also help use energy more efficiently. Let's try implementing this. Take a neutron star. This is what's left behind after a huge star reaches its end. Its tiny, incredibly dense version. These little neutron stars are often paired with the small and normal ones. Neutron stars have some insane gravity. This could help them provide the energy needed to push the whole system. So, if an extraterrestrial civilization decided to build a machine like this, they'd probably do that near a binary system like this. But would our extraterrestrial friends settle for basic binary systems? Actually, they could go even further, for a wilder, more efficient option – Black Widow pulsars. Ooh. This is the most dramatic type of a binary system. A neutron star spins with unbelievable speed and doesn't just hang out with its companion star, but slowly devours it. These two create such a thrilling gravitational dance, it's both destructive and beautiful. As the neutron star spins, it just keeps flinging torrents of high-energy particles right into space, and all of them clash with the fragile remnants of its poor little partner. Can you imagine that this energy could be harvested? All these options – hypervelocity stars, binary systems, and spider pulsars – would be great for this stellar engine project. A civilization that had this type of engine could gradually explore and colonize the galaxy, all while having its own energy source and planets with them. But how do we know whether these starships actually exist? Astronomers look for something called technosignatures. These are little clues and hints, something that looks unusual for normal celestial bodies. For example, things like weird motion in binary systems, or stars that eject material in weird, unnatural ways. They could all mean that there's some technology being used there. We haven't any evidence of that so far, but there are candidates. There are 2 Black Widow pulsars that look strange. Clement Vidal, the author of the paper, says that we should look at those systems closely, just in case. And even if it turns out that this idea is incorrect, we can still use it as an inspiration for ourselves. If extraterrestrial civilizations won't do this before us, we might just pioneer that technology. And speaking of technosignatures, besides these starships, NASA is also looking for signs of megastructures in space. Maybe other civilizations don't treat their stars as some sort of chariot horses, but simply use them as a giant energy source. Life needs energy to survive, whether it's microbes, animals, or smart human-like civilizations. As life evolves, its energy demands skyrocket. Now, we started with fire, then moved to coal and oil, and now we're exploring solar power. One day, we might start harvesting the power of our sun directly. Maybe advanced extraterrestrial creatures are already doing this. On Earth, a physicist, Freeman Dyson, proposed the idea of a Dyson sphere, a huge structure around a star that can harvest its energy, like one enormous solar panel, but right around the sun. Sounds crazy to us, but we might find it somewhere out there. Once again, astronomers are checking technosignatures to spot those. For example, they've analyzed data from over 5 million stars, trying to find weird signals, flickering, or anything that can't be explained by dust or similar stuff. If we're talking about a Dyson sphere, then eating a star's energy would make it radiate a lot of infrared heat. That means we'd notice a telltale glow. Eventually, they narrowed it down to 368 possible suspects. They checked those, and only 7 stars remained. These stars show strange light patterns that we really can't explain yet. These stars are mostly small, faint red dwarfs. One of them is especially famous, called Tabby star. It blinks and dims in weird random ways, dropping in light by 22% from time to time. Astronomers aren't sure whether it's some broken moon flying around it, dust, or a Dyson sphere. In any case, they'll keep looking for these techno-clues. Let's hope we'll learn the truth someday.
An ultra-powerful explosion happened just outside the Milky Way galaxy, kinda next door in cosmic terms, and it was unlike anything we've witnessed before. The thing kept blasting again and again, shooting out crazy strong bursts of energy called gamma rays. It was almost an entire day of non-stop firing back in July 2025. In gamma ray time, that's basically forever, because normally gamma ray bursts last from a few milliseconds to a few minutes, not hours on end. But the craziest thing is that this phenomenon might be linked to an elusive and mysterious kind of black hole, the existence of which we haven't proven yet. Scientists gave this phenomenon a complex sciencey name. Usually, these gamma ray bursts happen when a giant star goes off. One big dramatic exit, and that's it. But this space diva didn't get the memo and kept coming back for encores. NASA's Fermi telescope first spotted this bizarre space performance on July 2nd. But then some other space gear, the Einstein probe, realized it had already been blasting the day before. Scientists tossed around a few guesses. It could have been a massive star, like 40 times the size of our sun, that went out in a special kind of way. Not your average star demise, but one that somehow kept its cosmic engine running, like a car that won't stop even after the gas runs out. Another theory is even wilder. Some scientists think those space fireworks might have gone off when a star, likely a tiny one called a white dwarf, got shredded by a black hole. It's like a cosmic blender moment. They call it a tidal disruption event, or TDE. You see, not every star goes out with a giant boom like in the movies. Most just get old, puff up, and slowly fade away, leaving behind their tired little cores. Those leftovers are called white dwarfs, star corpses made of super weird squished up gas. You see, what happens to a star when it goes off depends on how big it was when it was born. Stars that start out kind of small, about the same size as the Sun or up to 10 times bigger, usually end up as white dwarfs. Most of the time, these stars run out of fuel and blow off their outer layers, creating a glowing cloud called a planetary nebula. What's left behind is the super hot dense core, about the size of Earth. That's the white dwarf. They're still really hot when they form and slowly cool down over time. After billions of years, they might turn into cold, dark, black dwarfs. But the universe isn't old enough for any of those to exist yet. Anyway, let's get back to our investigation. If this second theory is right, the black hole responsible for this cosmic show wasn't a regular one. To pull off something like this, it would need to be a super rare kind of black hole. One of those mysterious intermediate mass black holes scientists have been trying to find forever. Before we move further, let's take a look at the black hole lineup. Small ones are called stellar mass black holes. They're formed when massive stars weighing somewhere between 20 to 100 suns collapse. Supermassive black holes are real space behemoths. They're millions and even billions of times heavier than the Sun. They chill at the centers of galaxies. Even our home Milky Way galaxy has one called Sagittarius A star. This black hole is mostly dormant. It absorbs gas or dust only occasionally, but its estimated mass is millions of times that of our Sun. There might be one more type of black hole: primordial black holes. Scientists think they might have formed in the very first moments after the birth of the universe. That's when pockets of hot material could be dense enough to form black holes. Their masses might have ranged from 100,000 times less than a paperclip to 100,000 times more than that of the Sun. After that, the universe expanded and cooled very fast, and the conditions for forming black holes this way came to an end. These days, 13.8 billion years later, astronomers still haven't found definitive proof that those primordial black holes even existed. On the other hand, it's possible that they could have evaporated as space became older, due to certain processes happening at the edges of their event horizons, aka the points of no return. According to theoretical predictions, lower mass black holes with less mass than a mountain could evaporate more quickly than larger ones. If this idea is correct, then many of those early black holes have already completely dissipated. But more massive primordial black holes could still be lingering across the universe. Anyway, if we get back to the already proven kinds of black holes, between stellar-sized black holes and supermassive ones, there are elusive intermediate mass black holes. Scientists think they exist, but they're like Bigfoot. Lots of theories, not much proof. Astronomers think that small black holes might crash into each other and merge over time to form those medium ones, but spotting one is almost impossible. They're sneaky and silent. People often tend to mistake them for star graveyards, clusters of smaller black holes just hanging out. Sometimes, intermediate mass black holes even hide behind groups of stars that orbit them real close. The best way to catch such a black hole is to look for clues. Scientists measure the mass of black holes when they crash into each other, or spot them mid-meal when they're munching on a nearby star. So far, around 300 possible intermediate mass black holes have been found, but no one is totally sure which ones are the real deal. And now, astronomers think they've finally caught this super rare missing link black hole. Right now, it might be snacking on a poor star way out at the edge of some distant galaxy. In a study published on April 11, 2025, scientists talk about a black hole called HLX-1. It's hanging out about 40,000 light-years from the center of its galaxy and roughly 450 million light-years away from us. Using data from NASA's Hubble Space Telescope and the Chandra X-ray Observatory, the team spotted a bright flash. That very tidal disruption event that occurs when a black hole tears a nearby star to pieces. Then they ran computer simulations to recreate the whole thing, and it showed HLX-1 stretching the poor star like space spaghetti. By the way, this process is indeed called spaghettification. Astronomers have their own cosmic jokes, you know? Anyway, scientists first spotted something weird going on with HLX-1 back in 2009. NASA's Chandra X-ray Observatory caught a super bright glow coming from deep space. Turns out, it could have been another tidal disruption event. The glow from HLX-1 hits its peak around 2012, and it's been fading ever since. But of course, there's a catch. Nobody's totally sure it's a real intermediate mass black hole. You see, that light might not be from a shredded star at all. It could be from an accretion disk, a giant, super hot ring of gas and dust swirling around the black hole's edges. And the only way to figure out what's really going on is to keep watching. If the light keeps fading and doesn't flare back up, then yeah, that poor star probably got eaten. Intermediate mass black holes are a big deal because they're the missing link in the black hole family tree. The connect the dots piece in understanding how black holes grow up. There's also an idea that intermediate mass black holes might start out as big stellar mass black holes and just keep bulking up over billions of years until they become those massive, city-sized monsters at galaxy centers. That means most of their lives, they're probably lurking way out on the galaxy's edge. Like HLX-1, before they get launched into deep space. And now, some scientists think there could be a sneaky intermediate mass black hole hanging out on the outskirts of our Milky Way right at this moment. Even if there isn't, the research team is still keeping an eye on what's happening after that blast and trying to piece together what in the universe actually caused it. Next up on their to-do list is figuring out exactly where it happened. Once they pin down the location, they'll be able to measure just how much cosmic energy this thing pumped out and how big the explosion really was.
It happened long, long ago and far, far away from our planet, all the way across the universe. A powerful burst of gamma radiation lasted a mere half-second, but it released an enormous amount of energy. It was more than our sun would produce in 10 billion years. This brief flash lit up the whole sky. Afterward, a much softer and more long-lasting glow replaced it. Watching this fading light, astronomers on Earth noticed a strange infrared signal. It was invisible to the human eye, but could be perceived as heat. After examining the phenomenon with X-ray, radio, optical, and infrared waves, the astrophysics team made a shocking conclusion. It seemed that people had finally seen a newborn Magnetar for the first time ever. This Magnetar was likely formed after two neutron stars had merged. It resulted in a kilanova, one of the brightest and largest stellar blasts. Its light finally reached our planet on May 22nd, 2020. But I'm getting ahead of myself. How about we first figure out what these novas, magnetars, and neutron stars are? Imagine a massive star, at least 5 times the mass of our sun, reaching the end of its life. It might be because it's run out of nuclear fuel. If it happens, the star starts to cool off. The pressure inside drops, and the gravity starts to squeeze inward. And then, more than 1 million times the mass of our planet collapses within 15 seconds. It happens so fast that an enormous shock wave causes the outer part of the star to blow up. It produces a blinding burst of light. This powerful blast is called a supernova. What's left behind is an incredibly dense core with a huge cloud of hot gas, called a nebula, expanding around it. If the star has been massive enough, more than 10 times the size of the sun, it's likely to turn into a black hole. By the way, when a star similar in size to our sun runs out of its fuel, it turns into a white dwarf. It expels most of its outer material, and only the star's hot core remains intact. Such a core usually gets heated up to 180,000 degrees Fahrenheit. A white dwarf is just a bit bigger than our planet, but half as massive as the Sun. In other words, these stars are some of the densest objects in the universe. A white dwarf can be 200,000 times denser than the Earth. It usually takes a white dwarf over 1 billion years to cool down. Under certain conditions, such a star can erupt, and this event is called a nova. It's way less bright than a supernova or even a kilanova, which occurs when two neutron stars, or a neutron star and a black hole, merge into each other. Anyway, back to a supernova. If a star's large but not massive enough to turn into a black hole, it turns into a neutron star. It's basically a giant nucleus, the central part of an atom. These stars are mostly made up of neutrons and are rarely larger than 20 miles across. For comparison, our Sun is almost 865,000 miles across, which is 109 Earths put side to side. But don't let this relatively tiny size fool you. Any neutron star is at least 1.5 times heavier than our Sun and has an intense magnetic field. If you scooped just a teaspoon of this star's insides, this matter would weigh more than 1 billion tons. That's so dense that it makes neutron stars some of the most extreme objects people know about. The next stop is the black hole itself. When two neutron stars merge, they most often create a new, much heavier one. Within milliseconds, or even less, this star collapses into a black hole. But the astronomers who examined the flash of light recorded in March think there might be another outcome. They're almost sure they saw something never observed before: the birth of a magnetar. That's an exotic form of a neutron star with an ultra-strong magnetic field. It's 1,000 trillion times stronger than our planet's. This field is also so powerful, it heats the star's surface up to 18 million degrees Fahrenheit. Neutron stars are weird and scary. Their interior is a never-ending dance of particles in extreme conditions. It results in unexpected and odd structures. For example, closer to the surface, hundreds of neutrons form blobs. Those are not unlike some weird kind of space nochi. They mold into long chains once you go deeper. Not that you'd ever be able to explore a neutron star from up close. These long chains look like a layer of spaghetti. Underneath, there's a region of even more extreme pressures. That's where our spaghetti turns into lasagna sheets, since we've started on this pasta comparison. Finally, under all these layers, even lasagna loses its form and becomes a shapeless mass. But even in this mass, there are some tube-shaped gaps. And don't they look like ziti? Another thing about neutron stars, they're spinning non-stop. And this spinning is fast, more than several hundred times per second. The fastest spinning neutron star makes more than 700 turns per second. That's 42,000 times per minute. Neutron stars also have incredibly strong magnetic fields. That's why, if there was life on a neutron star, it would be two-dimensional. The star's gravity is so powerful, it'd literally flatten anything on its surface. And if such a star had an atmosphere, it wouldn't spread up further than a foot or so above the surface. But if neutron stars are bizarre and spooky, magnetars are too, perhaps even more so. Thanks to their incredible magnetic pull, these stars would win in the strongest magnetic field competition, hands down. To put it simply, magnetars are the most powerful magnets in the universe. Their magnetic fields can seriously mess with the neighborhood. Atoms, unlucky enough to get close to such a star, get stretched into pencil-thin lines. If you somehow found yourself several hundred miles away from a magnetar, it would end badly for you. The magnetic field would first disrupt your bioelectricity. It means that your nerve impulses wouldn't work anymore. But that's not all. Even your molecules would change under the influence of the star's field. In the end, you'd kind of vanish. If a Magnetar flew within 100,000 miles from our planet, it'd wipe out the data on every single credit card in the world. Astronomers have seen Magnetars before, but they've never witnessed one getting born. After the light was first detected, scientists understood something didn't add up. They compared different kinds of observations. It turned out that the light spotted by the Hubble Space Telescope was 10 times brighter than predicted. This information made the scientists think outside the box. They realized an entirely new phenomenon was going on. The team had several ideas that could explain the bizarre brightness, but the most probable one was also the most eccentric. Before, scientists thought magnetars only appeared after massive stars exploded and left behind super-magnetized neutron stars. But now, they suppose a small number of magnetars may actually appear in a more peaceful way after two neutron stars merge. Scientists only know about no more than 10 magnetars in our home Milky Way galaxy. They don't know for sure what makes these stars so terrifyingly magnetic. Whatever it is, magnetars don't seem to last long. After 10,000 years or so, they return to a more familiar neutron star state. They're still extremely magnetic, super dense, but not so extreme. The closest magnetar people know about is 9,000 light-years away from Earth, in the constellation Carina. Astronomers think the original star was 30 to 40 times the mass of the Sun, which is a really big one. Another magnetar is 18,000 light-years away from our planet. It suddenly started to burst in 2002. Around 80 bursts were recorded within a 4-hour window. After that, the magnetar has never been active again. By the way, the researchers were also immensely excited about seeing a kilonova. It occurred when the two neutron stars supposedly merged. A kilonova is more than 1,000 times brighter than a typical nova. Before, astronomers had only one confirmed and examined event of the kind. But the kilonova recorded in March looked different, and it might allow scientists to explore the diversity they knew nothing about.
Right after its creation, the cosmos was shrouded in darkness. I mean, I wasn't there, but that's what most scientists are thinking. All of the stars were hidden behind a thick cloud of primordial gases. Then, all of a sudden, something cleared up this fog, and the universe started shining as it finally woke up. But how did this happen? 8 faint, recently discovered galaxies might hold the answer. The Big Bang created our world around 13.8 billion years ago. At first, it was just a super hot and chaotic boiling soup of particles. But over time, things cooled down, and particles could finally stick to each other. That's how the atoms appeared. Some helium, but mostly hydrogen, the very first element. And these first elements started creating thick gas clouds, which were very opaque. Then the first stars started forming. They were incredibly bright, emitting lots of light, including ultraviolet radiation. But even though these stars were shining, much of their light couldn't travel far because of that nasty hydrogen fog. The gas clouds absorbed and scattered any little light particles around. It was like the light was trapped around the stars. The Dark Ages lasted for hundreds of millions of years. Then, everything changed. Recently, the James Webb Space Telescope has spotted ancient dwarf galaxies from that epoch. Turns out, they're the ones we should be thanking for lighting up the universe. Back then, they were filled with early stars. These stars emitted tons of radiation that was so powerful that it managed not to just overcome, but break apart the hydrogen atoms in the fog. It turned them into charged particles, like particles that carry a little bit of electricity called ions. Little by little, the fog was cleared away. This process of clearing out the fog is called reionization, and this beautiful time is known as the epoch of reionization. Finally, the light was able to travel to all corners of the universe, which was a game changer, just like humans' Age of Enlightenment. To find these little igniters, astronomers used a technique called gravitational lensing. Imagine light traveling through space like a straight beam. But just like everything in our world, even time, light obeys gravity. If it's too strong, it'll literally bend the light beams. So when the beams pass near a massive object, the object's gravity pulls on them, curling and twisting their path. That's why black holes look so creepy, as they stretch stars and space around them like some whirlpools. But it's not that creepy. A regular glass or magnifying glass does something similar, hence the name gravitational lensing. When the lensing object is horrifyingly massive, it bends the light into multiple images of the same object, creating a creepy and mesmerizing structure called an Einstein ring. But if it's not that big, then the bending is less dramatic, and it just slightly distorts the shape of the background object, making it look kinda stretched. Gravitational lensing also helps scientists study things like the spooky dark matter. If the light looks stretched, and it's not just because of some obvious massive objects nearby, then it might be something invisible and heavy bending it. Since these 8 galaxies were too faint, no wonder they're almost as old as my unread emails. Scientists had to use these gravity tricks to observe them. The team studied light from galaxies that are over 13 billion years old. Finally, they focused on a galaxy cluster called Abell 2744, also known as Pandora's Cluster. And these findings helped them understand how even little fellas played a huge role in transforming the early universe. The James Webb Telescope is an incredible tool, and soon it might help us look at even earlier times, at the cosmic dawn, when the universe was only several millions of years old. Another great tool, called the Roman Space Telescope, is going to help it. It's also possible that these galaxies weren't the only helpers in this entire saga. These early massive stars were absolutely terrifying. They just don't make them like that anymore. Some estimates suggest they were 30 to 300 times more massive than our Sun, and millions of times brighter. Modern stars have some heavier elements in them, but back then, they used only the stuff available, hydrogen and helium, which is why they were so hot and shiny. But they also had very short lifespans, lasting just a few million years. For example, our Sun is 4.6 billion years old and is still going strong, thankfully. At the end of their lives, they went supernova. These colorful bursts of energy were so strong that they forged the first heavier elements in our world and spread them across the universe, planting first seeds for the future planets. Meanwhile, the stars themselves didn't just disappear. They collapsed under their own gravity, creating the first black holes. Now, the black holes are also known for producing insane amounts of radiation, so it's possible that they might have helped speed up the clearing of the fog. Ironically, they help the universe shine brighter while sucking up the light at the same time. Recent discoveries show that black holes might be much older than we used to believe. They probably helped new stars and galaxies form. They were millions or even billions of times the mass of the Sun. The James Webb Telescope has already found a pair of early quasars. That's what we call the bright centers of galaxies powered by supermassive black holes. It's a curious pair of quasars that are merging just 900 million years after the Big Bang. This might be the earliest and most distant pair of merging quasars ever found. The telescope has also been studying things that are called cosmic lighthouses. In scientific language, they're pulsars. Pulsars are super-dense remnants of massive stars. They form from stars that were once 4 to 8 times more massive than our Sun. One of the greatest things about them is how fast they spin. They're one of the fastest objects in the universe. They might do around 700 rotations in just 1 second. They got their name because they behave like lighthouses, basically flickering radio waves. These beams of radiation sweep across the sky, creating a pulse-like signal that we detect. Now, a star basically works like this. There's nuclear fusion happening inside of its core. Atoms get fused in each other, move at crazy speeds, bump, all meanwhile releasing an unbelievable amount of energy. That's why they emit tons of light and heat. Of course, all this pressure tries to push outward, sweating like crazy to expand a star. The greatest the fusion is, the more powerful and insane the star gets. On the other hand, there's gravity that's pulling inward, trying to compress the star and keep it a nice small dense ball. As long as there's balance, the star keeps living, but when it gets old and spends all of its nuclear fuel, it becomes too weak to generate the energy it needs and can't fight against gravity anymore. That's when it basically collapses under its own weight, going supernova. What's left behind is the star's core, but now it's crushed down to an incredibly small size, about 12 to 17 miles across. It's roughly the size of a city. This dense core is known as a neutron star. The material in a neutron star is so dense that just a teaspoon of it would weigh as much as 4 billion tons, like 10,000 Empire State Buildings. And all this collapse sets off a trigger, causing the neutron star to spin super fast, creating a pulsar. It's kind of like when an ice skater spins faster when they pull their arms in. Pulsars often have a smaller star friend orbiting them, although it's not always a friendly relationship. Not long ago, astronomers discovered a pulsar that was surrounded by lots of energetic material for some reason. They realized that all this material was the remnants of another much larger star. Turns out, the pulsar had been slowly destroying its friend with its terrifying radiation and particles until it basically ate the neighbor away. It's similar to how a black widow spider consumes its mate. So, systems like this were called black widow pulsars. In any case, these lighthouses most likely help the reionization process as well. A long time ago, they could be very energetic stars in small galaxies and could emit enough radiation to transform the early universe. The James Webb Telescope's mission is to find more of these lighthouses and see what role they played in the universe's evolution.
Spotted. It seems like two giant stars were caught in the middle of a romantic kiss. This sounds a little bit like paparazzi fodder at first, but we're actually talking about a cosmic twist an international team of astronomers has discovered. So, the life cycle of a solo star is relatively simple. They're born in vast, gassy areas of space, burn through their fuel, and at some moment, they explode as supernovae. But when stars are born relatively close to each other, their gravitational pull can cause them some troubles and captivate them into what seems like an eternal dance. In some moments, they come so close to each other that they're practically touching. These stars may spend billions of years circling each other, but their kiss lasts for a few million years only, which is just a blink of an eye in cosmic terms. The lead author of this study was on a mission to find these binary stars caught in such a cosmic kiss. He focused his search on the Tarantula Nebula, a beautiful star-forming region located in a large Magellanic Cloud, which is 160,000 light-years away from our home planet. And there it was, the shiny double star system that stood out from the rest. The two stars found there were pretty big and nearly the same size. Together, they make a mass of about 57 times larger than that of our Sun. Before this, we discovered only 3 other binary systems with a large mass. And since these two stars were so close to each other, they created an intense gravitational pull. This made them orbit each other at a staggering rate of once a day with their centers a mere 7.4 miles apart. With the stars being so close, they formed a bridge where their fuel could mingle, allowing for around 30% of their total volume to be shared between the two. Temperatures of this system were crazy too. At first, it seems the internal mixing of their energy might make these stars live longer, as it allows for more fuel to be burned and for longer periods of time. But this is just a temporary benefit. There are 2 most likely scenarios for the star's ultimate fate. They could merge to form one giant star, which would eventually explode into a supernova. Or they could each explode separately and live out their remaining years as black holes orbiting each other. If they merge, this process would probably take around 600,000 years, while if they become binary black holes, they could continue burning for another 3 million years. But both scenarios would ultimately lead to their destruction. Unless the stars could end up as two separate black holes drifting away from each other through the vastness of space, there's a possibility for that to happen too. There's something spectacular stargazers across the globe could see recently. Jupiter and Venus, the two brightest planets in the sky, ended up so close it appeared like they were about to collide, or as if they were kissing too. At least that's what it looked like from here on Earth. In real terms, they're still 400 million miles away from each other. Here's another interesting thing astronomers like to talk about: G-objects. Those are celestial objects that look like clouds of dust and gas, but behave like stars. At the center of our galaxy, there's a supermassive black hole. It's 4 million times the mass of our Sun, and recently, scientists found out there are two mysterious G-objects that hang out pretty close to that black hole, so-called G1 and G2. And the most probable theory is that G2 are two stars that were orbiting the black hole in tandem and merged into an extremely large star cloaked in unusually thick gas and dust. During G2's closest approach to the black hole, it showed a strange signature. It was elongated, and much of its gas was torn apart. As it got closer to the black hole, it lost its outer shell, and now it's getting more compact again. The thing that has everyone excited about the G-objects is the material that gets pulled off of them by tidal forces as they sweep by the central black hole. This material must inevitably fall into the black hole, and the result is an impressive fireworks show. This happens because the material eaten by the black hole will heat up and emit radiation before it disappears across the event horizon. An event horizon is that scary boundary around a black hole from which nothing can escape. Now, it seems scientists have discovered 4 more G-objects, and they're all located within 0.13 light-years of this black hole. And it could be that all of the 6 objects used to be binary stars that got together and merged because of the powerful gravity of this giant black hole. Usually, it takes over 1 million years to finish the merging process between two stars. We definitely want more G-objects because it's one of the rare opportunities for us to study how things behave near a supermassive black hole without being swallowed. Yet. Have you heard of variable stars? Look up at the sky. We often think of the stars as unchanging, eternal lights. Yes, some stars might appear constant, but others change in brightness over time, which is why we call them variable stars. Some of them dim and brighten again over days, months, or even years. We can't see it with the naked eye. We're talking about changes astronomers can only notice using equipment and over longer periods. And how about vampire stars? Imagine 2 stars, a red giant and a white dwarf, in a binary system, swirling around each other like cosmic ballet dancers. The red giant, which used to be a vibrant and fiery star, now has aged and grown tired. Its outer layers of hydrogen, which were once held tightly by its gravity, have now weakened, making it vulnerable to the smaller, denser white dwarf. The white dwarf, known as the vampire star, thirsts for the hydrogen fuel that its larger sibling holds, and it sees a great chance there. As they spin together, the vampire star uses its powerful gravitational force to steal the hydrogen from the red giant's outer layers. The vampire star glows with a blue hue, looking full of energy and more youthful and vibrant than its aged dancing partner. Not only vampire stars, the horror continues with zombie stars too. Sometimes when the red giant explodes, it doesn't completely break up into smaller pieces. Instead, a white dwarf remnant is left behind. It's basically a zombie star that was gone at the moment, but has risen back to life. But this isn't your average zombie, hungry for brains. No, this star hungers for the very substance that its vampire sibling had been taking from it all along: hydrogen. And if the zombie star is close enough to its victim, it will start sucking material back in to start its core again. It will become a hydrogen explosive, ready to go boom in a spectacular show of cosmic revenge. It's a fascinating phenomenon. We usually won't even manage to detect it, because these explosions are much fainter than the usual supernovas. But when it does happen, the resulting blast is truly epic. And it destroys both the vampire star and its zombie sibling. It seems vampires and zombies may not be a work of fiction after all. Not only are we made of stardust, but we're also more similar to stars than we thought too. For example, stars also like to hang out with their close group of friends. Most stars prefer to travel through the universe in clusters. It's a group of stars that end up bound together by gravitational force. The stars in the cluster are mostly made of the same age and type, hobbies, and interests. I guess even they have better social lives than I do.
So astronomers have spotted about a dozen mysterious explosions in space, and no one really knows what they are or why they're happening. At the moment, they occur about 200 million light-years away. But what if, one day, they get much closer to our planet? Now, this all started back in 2018. One day, telescopes saw a giant boom far away in space. That explosion was incredibly bright, about 100 times brighter than a normal star explosion, called a supernova. The strange thing was that normal supernovae take weeks or even months to fade away. But that one went from kaboom to poof, gone, in just a few days. It got extremely hot and huge, about the size of our whole solar system, and then vanished like it never happened. Scientists were seriously confused. Now, they named the explosion the Cow, because its official name was too long and not exciting at all. Since then, astronomers have been hunting for more of those oddball explosions. And indeed, they've found a few more and given them weird animal names too. That's how we got the koala in 2018, the camel in 2020, the Tasmanian devil in 2022, and the finch, or the fawn, in 2023. All of those are part of a strange group called LFBOTs. That stands for Luminous Fast Blue Optical Transients. Luminous means they're super bright. Fast because they happen and disappear really quickly. The blue color results from their temperature. They're super hot, like 72,000 degrees Fahrenheit. And optical transients means they show up in visible light and don't stick around for long. Even now, the scientists are still scratching their heads, trying to figure out what's causing these bizarre space flashes. It's like the universe is playing a mysterious game, and no one knows the rules yet. At first, scientists thought those space explosions were failed supernovae. That's when a star tries to explode but instead collapses in on itself, kind of like a balloon popping inward. That collapse can create a black hole in the middle that will eat the star from the inside out. But recently, a new theory has popped up, and it's even cooler and creepier. It has to do with black holes, super squished leftovers from exploded stars. They're so powerful that even light can't escape their clutches if it gets too close. That's why they're totally dark and impossible to see directly. Now, some space scientists think that unknown black holes, not too big and not too small, might be pulling in stars that get too close, which produces those explosions. Such holes are called intermediate mass black holes, and no one has actually seen one of those yet. They're like space's biggest mysteries, and we'll try to solve it in a few minutes. But after that, you need to know that a new LFBOT has shown up in space. It was spotted by a telescope in Liverpool and is currently called AT 2024 WPP. Yep, scientists still haven't picked an animal name, but they're thinking maybe the wasp. What do you think of this name? Share it in the comments. Anyway, one of the scientists is sure that it's the best one since the cow. The most recent space explosion is super interesting and extremely bright, like me. Maybe the brightest one since this whole LFBOT thing began in 2018. This new WASP boom also doesn't look like a failed supernova. And still, scientists are checking all the data just to be sure. Now, scientists are pretty sure mid-sized black holes that could cause the explosions must exist somewhere. It's like knowing a secret creature might be hiding in space, but no one has gotten a photo of it yet. Some scientists think that this idea is the most exciting, and that it might even help explain dark matter, one of the biggest mysteries in the entire universe. Well, whatever the truth is, a recent discovery might shed light on the existence of mid-sized black holes. The thing is, when it comes to black holes, space has a few different sizes: small, super huge, and something in the middle. The small ones are called stellar mass black holes. They're around 5 to 50 times heavier than our Sun. The giant ones are called supermassive black holes. Makes sense. They're millions or even billions of times heavier than the Sun. They usually hang out in the middle of galaxies. And then there's the mysterious kind in between, called intermediate mass black holes. Those are like the missing link of black holes. Scientists are pretty sure they should exist, but we barely know anything about them, like where they came from, how they grow, or what they're made of. Good news, that mystery might finally be getting solved. Thanks to several new studies, scientists now have some exciting new clues. Researchers have found waves in space, which are called gravitational waves, that seem to come from black holes smashing into each other. And not just any black holes, but ones that are 100 to 300 times heavier than the Sun, which may mean that they're those mysterious mid-sized black holes. Plus, those are the biggest black hole collisions we've ever recorded on Earth. Now, black holes are like space fossils, super old history clues. And those newly discovered black holes could tell us about the first stars that ever lit up the universe. The problem lies in the fact that our tools on Earth, like LIGO, which stands for Laser Interferometer Gravitational Wave Observatory, only catch a tiny moment of these black holes crashing together, literally just a split second. That makes it tough to figure out where those medium-sized black holes come from. So, scientists have a new plan. One scientific lab is getting ready for a future space mission called LISA, short for Laser Interferometer Space Antenna. It's a cool space project by NASA and the European Space Agency, launching in the late 2030s. LISA will float in space and be able to catch the whole story of black hole crashes, not just the final boom. It will track black holes years before they crash into each other. And, if all goes well, we might finally figure out where these mysterious black holes come from and learn even more about how our universe began. So you might be wondering about how LISA will do it. Remember we talked about ripples dashing through space called gravitational waves? Black holes crashing into each other could send them out. Well, LISA is being built to listen for such waves. It'll float in space and look for all kinds of cosmic shakeups, not just huge ones, but also smaller black holes spinning around giant ones. Now, why do gravitational waves matter? A lot of space stuff is too dark to see with regular telescopes, since no light comes from it at all. But gravitational waves don't care about light. They go through everything, telling us about the secrets hiding in the dark parts of the universe. By studying them, scientists hope to learn about things we've never seen before, like black holes, or what really happened at the very start of the universe, and maybe even things we don't know exist yet. LISA will help us figure out how the universe began, how it's changing, and what it's made of. Now, getting back to those black hole collisions, finding them isn't easy. But researchers have come up with a smart solution. They're using artificial intelligence to make sure the signals from space aren't messed up by noise from Earth or the machines themselves. This work was part of a project focused on combining AI with space science. Scientists are getting more confident that intermediate mass black holes, the ones in between small and supermassive, are real, and they might be some of the most exciting things we can study using gravitational waves, both from Earth and from space. So the next big step? Looking to the Moon. Future detectors place on the lunar surface could be even better at catching certain types of space waves, especially ones that Earth-based machines might miss. That would help scientists figure out where those black holes dwell in space. Besides this research, scientists are also planning human exploration of the moon. They're helping NASA choose the best spots for future missions, focusing on big science goals like solar physics, space weather, and how the universe works. Right now is a super exciting time, not just for studying black holes, but also for connecting space exploration and science.
Recently, the James Webb Space Telescope has spotted something no one expected to see. It might be a new kind of star that was born in the early universe. And the most shocking thing about this star is that it's likely to be powered by dark matter. The thing is, around 84% of matter in the universe doesn't emit or absorb light. Astronomers call this stuff, which can neither be seen directly nor detected by indirect means, dark matter. It supposedly affects visible matter, radiation, and the very structure of the universe. These days, we have several detectors looking for weakly interacting massive particles. That's what dark matter might be composed of. But so far, researchers have found nothing of the kind. One of the most recent studies claims that dark matter might produce long, fine-grained streams radiating out from Earth like hairs and streaming throughout the universe. But it hasn't been proven yet. Now, returning to dark stars that might be powered by this mysterious dark matter. The very concept of such stars still remains hypothetical. Astronomers aren't sure that the images received by James Webb show exactly them. But even if one of the three candidates spotted by scientists turns out to be this new kind of star, it could offer us a glimpse of how stars formed in the early universe. Plus, we would probably be able to find out something new about dark matter and even explain how supermassive black holes appeared out there. The first time someone mentioned the term dark star was in 2007. These space objects could have been some of the first types of stars to form in the universe. They haven't been observed yet, but astronomers think they might be powered by heat that is generated during dark matter interactions rather than by nuclear fusion reactions, like it happens with our sun. Experts believe dark stars would probably look extremely weird. They could have appeared from clouds of hydrogen and helium that drew in excess dark matter. We still don't know the nature of dark matter. But there's a theory that particles of dark matter might be able to interact with themselves, annihilating one another during collisions, and, thus, producing huge amounts of light and heat. Then, this heat could have prevented the cloud of hydrogen and helium from condensing. It means these gases wouldn't have been able to create dense, hot cores similar to those the stars existing today have. And if this gas cloud wouldn't have condensed, dark stars could have grown to truly enormous size. In theory, a dark star could be around 10 times as wide as our planet's orbit around the sun. Imagine the sheer size of such a space monster. These stars would also be millions of times as massive as our star, and their light could be billions of times brighter. It might be the reason why James Webb managed to spot them. To check for dark stars that might be lurking out there, scientists thoroughly examined the images from a JWST survey of early galaxies. They spotted more than 700 objects that could have appeared in the first 100 million years after the universe appeared. That's exactly the time when dark stars were probably born. Light from objects that appeared so unimaginably long ago is stretched, or, as astronomers call it, redshifted. So, the team examining the images picked 4 objects that had already been confirmed to be extremely redshifted. It meant that the researchers were looking at some of the oldest space objects observed so far. These objects might be tiny galaxies from the times when our universe was just a baby. Unfortunately, since they're so far away, the resolution of James Webb isn't enough to figure out whether they're indeed galaxies or just large super bright stars.
More than 1 million Earths can fit in our sun. New research shows that between 20% to 35% of suns eat their own planets, and a quarter of planetary systems orbiting stars like the sun had a chaotic past. The very thing that gives life can also take it away. All the planets in our solar system revolve around the sun. and they all do it in a somewhat consistent way. It's most likely that they stayed that way ever since they first came into the picture, but not all of them. This chaotic existence means that a solar system had a lot of planets in the litter until the host sun decided to melt them away. Our solar system is panned out perfectly so that no planet's gravity interferes with each other. The gravitational force on Jupiter is a lot tougher than Earth's, which means that if Earth gets close to Jupiter, we'd be another moon for Jupiter. The planet is so big that if Earth were the size of a grape, Jupiter would be the size of a basketball compared to it. Even with the best technology in the world, it's difficult to tell if stars do, in fact, eat their planets. The best way to study this is to observe binary systems. That's just a sciencey way of saying a system with two stars orbiting each other. Usually, the two stars were formed around the same time from the same gases and the same conditions. It means they should contain the same elements, more or less. When you open your eyes in the morning, the sunlight that's been traveling for millions of miles greets you. The closer we get to it, the hotter it is. But the rays traveling from the sun also contain certain chemicals that make it unique. The chemicals that are associated with the sun are light materials like oxygen, carbon, hydrogen, and helium. You can find some other stuff in it too, but these are the main ones. By studying these elements, you can learn the history of a solar system with enough detail to determine if it was chaotic or smooth. Scientists studied 107 binary systems composed of suns like ours by analyzing the light. Since each system contains two suns, they compared and contrasted them to see the differences. They observed the stars with a thin outer layer, having different elements than their companion. All suns contain light elements, but there are some that have rocky elements, like iron, silicon, and titanium near the sun. These elements are associated with rough terrains that you'd find on the surface, but they're out there floating in the middle of space. The thinnest outer layer is especially rich in iron compared to the other layers. Many stars are twins at birth. Even most of the Milky Way stars have a buddy in a binary system. It means our sun is pretty unique for not having a partner. But there are some theories out there that suggest that the sun may have lost its twin in the past. It's around 184 light-years away and is called HD 186302. This might be our lucky star. A stellar nursery is where thousands of stars are born. They're made up of gas and dust that gradually collapse under their own weight. Our sun may have started in such a way 4.6 billion years ago. And when they're mature enough, they go out into the open, usually with their travel buddy. Actually, scientists claim that up to 85% of all stars could be in binary pairs or have more buddies, but over 50% are dual pairs. The only problem is that we can't really see it, since it strayed from its original orbit an eternity ago. But traces of it can be found in the Oort cloud. That's the vast cluster of space consisting of comets, space rocks, and ice in the outer edges of our sun's reach. They float around quite a lot, since they're far off the sun's gravity and can easily be knocked out of their orbit into open space. Flying through such a space is no different than flying through any random void of space. The reason why some of these light elements in space contain rock elements you'd find on the surface of a planet is because the sun knocked them off their orbit and devoured them as they got closer. It also happens when a star becomes too big in its place and starts eating everything around it. According to scientists, if a star eats a planet, it can make it go chaotic and spin so quickly that it eventually rips apart. But don't worry, there's a very low chance of the sun devouring the planet in the near future. Stars are formed when a huge cloud of hydrogen and helium grows until it collapses under its own weight. The pressure increases and reaches extreme heat levels we can't even measure. Eventually, the hydrogen atoms lose their electrons, causing the hydrogen to fuse together and release energy, countering the gravity collapsing. But when the gravitational force overpowers the hydrogen fusion, the star begins to expand and becomes a red giant. And then, after around 1 billion years, the hydrogen in the outer core will go away, leaving plenty of helium hanging around, which will fuse with the rest of the elements around. And once all the helium disappears, gravity will shrink the red giant into a white dwarf. And when it's completely gone, the remains of the star release tons of gas and dust into space. Scientists claim that our sun has between 7 to 8 billion years left before it reaches that stage. But even if that becomes a reality, it wouldn't happen overnight. Something like this takes millions of years to take place. But what if the sun decided to devour us overnight as we speak? The planet would start feeling hot in seconds. Every slight degree change can lead to some catastrophic events. Ice caps can melt in a matter of seconds and flood the coastal lands. Even little islands in remote areas of the world will be submerged. And as it gets hotter, every snow-capped area will melt instantly and turn into desert-like climates. Some places will burn, and your everyday objects will melt on the spot. The Earth's interior will also get hotter, allowing volcanic eruptions to happen across the world. Antarctica will melt from the heat, as well as the volcanoes erupting inside. And just in a matter of minutes, the whole planet will turn into fire and ash before it explodes into tiny bits floating in space, reaching areas we've never even heard of. But no worries, something like this won't really happen. In case the sun knocks us off our rotation, the results would be different. It'll also get hot because the magnetic field around us protects us from the sun's radiation. And once we get knocked out of place, the magnetic field gets tarnished, and the extreme heat from the sun will boil us. The gravitational force will be unstable, so the physics of our everyday life will be chaotic. We'll have to wait 5 billion years from now when the sun turns into a red giant. It'll grow in size, eventually eating up Mercury and Venus. Chances are, Earth will also be on the menu. If Earth were to move only 900,000 miles closer to the sun, then it would be uninhabitable. It may seem like a lot, but it's only 4 times the distance between the moon and Earth. Detecting the chemical composition of the sun rays in solar systems that are further away could help scientists find other Earth-like planets. Since the atmosphere around these planet-eating stars changes the chemical composition, we can detect which solar systems out there have had a calm past. The main thing we have to observe is if the planets have a healthy orbit cycle. With nothing else getting in the way, we can assume that the planet could follow the same steps as Earth did for humans to be here. But this process will take ages, since there are millions of nearby stars similar to our sun. The odds of finding a planet similar to ours are near impossible at this rate. But if so, then there might be life on those planets. There will be no way of knowing if it's intelligent life, but they might have had the same evolutionary fate as us.
Now see here, astronomers have recently discovered a neutron star, also known as a dead star, spinning at an extraordinary speed of 716 times per second. It makes it one of the fastest spinning stars we've ever found in the universe. And it's not just about its speed. The surface of this neutron star is erupting with super powerful explosions almost non-stop. But before we dig deeper into the mystery of this neutron star, let's figure out what these stars really are. They form from the remnants of massive stars that are at least 8 times the mass of the Sun. When such stars exhaust their nuclear fuel, they can no longer counteract the force of gravity pulling their matter inward. This leads to the collapse of their cores, triggering a massive supernova explosion that blows away the outer layers of the star. What's left behind is an ultra-dense core. That's a neutron star. These stellar remnants are incredibly small, typically just 12 miles wide. At the same time, they pack in more mass than the Sun. The density of neutron stars is also overwhelming. Imagine taking the mass of 2 suns and squeezing it into a sphere about the size of a city. A single teaspoon of neutron star material would weigh around 10 million tons. That's the same as the combined weight of 85,000 blue whales. Such an extraordinary density is what gives neutron stars their immensely powerful gravitational fields. When matter falls onto a neutron star, it accelerates to speeds of millions of miles per hour before slamming into the surface. The energy release from such impacts is truly astonishing. Now, despite its name, inside a neutron star, there are not only neutrons. A few protons survive down there too. Now, normally, protons repel each other since they have the same positive charge. But in a neutron star, that crushing gravity forces them so close together that the strong nuclear force takes over. It pulls them toward the neutrons like they're all part of the same team. Inside the star, things get stranger the deeper you go. Near the surface, neutrons clump into blobs, kind of like a neutron gnagi. A bit further down, these blobs link together into long chains, forming what scientists call the spaghetti layer. I'm getting hungry. At even greater pressures, the spaghetti chains fuse side by side, creating flat sheets. Think neutron lasagna. Keep going any deeper, and the lasagna eventually breaks down into a uniform mass. But even then, the structure isn't smooth. There are gaps, long tube-shaped voids that look a lot like penny pasta. So, inside a neutron star, you've got layers of gnocchi, spaghetti, lasagna, and penny pasta. And each of them represents the mind-bending results of physics under insane pressure. Okay, I'm definitely having Italian for lunch today. Now, the recently discovered neutron star is part of a binary system located in a dense star cluster. This cluster is situated near the center of the Milky Way galaxy, approximately 26,000 light-years from Earth, in the direction of the Sagittarius constellation. The record-breaking spin of the star is extraordinary. If we take a period of not a second, but a minute, it'll be over 42,000 revolutions per minute. At the same time, the newbie ties with another neutron star, which spins at the exact same speed. Such extreme rotation rates are rare and make these stars cosmic outliers in terms of behavior and properties. Oh wait, we can't but mention our neutron star's binary partner. It's a white dwarf, a dense remnant of a star similar in size to our Sun. This white dwarf is pretty fast too. It orbits the neutron star once every 11 minutes. This makes the couple a binary system, with the shortest orbital period ever observed. Imagine a stellar object zipping around its partner faster than the time it takes to prepare a cup of coffee. Yep, that's the kind of speed we're talking about here. This tight, rapid orbit shows how powerful gravitational forces are inside the system. So, you might be wondering what makes neutron stars spin so rapidly. It's something called the conservation of angular momentum. Let me explain. When a massive star collapses into a neutron star, it shrinks dramatically. Such a rapid compression gives an instant boost to its spin. It's like an ice skater spinning faster when they pull their arms inward. And the smaller the star gets, the faster it spins, which results in extreme rotation rates. In binary systems like this one, neutron stars can achieve even faster spin rates. Their trick is to steal matter from their companion stars. This process is called theft. No, accretion. The stolen matter carries that very angular momentum, which adds to the neutron star's rotation speed. The accreted material can also build up on the neutron star's surface, eventually. It triggers powerful thermonuclear explosions. They release immense amounts of energy, temporarily making the neutron star shine up to 100,000 times brighter than our Sun. It allows astronomers to study the intricate details of these extreme environments. NASA's X-ray instrument on board the International Space Station, officially called the Neutron Star Interior Composition Explorer and thankfully nicknamed NICER, observed 15 thermonuclear explosions on the surface of our neutron star between 2017 and 2021. One of those bursts displayed a unique pattern called thermonuclear burst oscillations. Those are highly asymmetric patches of brightness on the burning surface layers of accreting neutron stars. This pattern matched the spin rate of the neutron star and thus confirmed its extreme rotational speed. But wait, the best part is coming. While neutron stars are already extreme, there's another class of them that takes things to a whole new level – magnetars. Now, magnetars are neutron stars with unimaginably strong magnetic fields, up to 1,000 trillion times stronger than Earth's magnetic field. These fields set them apart from other neutron stars. They can distort atoms in nearby objects, making life impossible anywhere near them. As for the energy density of a magnetar's magnetic field, it's so high that it's 10,000 times greater than the mass density of lead. Magnetars also produce bursts of X-rays and gamma rays that are so powerful they can temporarily outshine entire galaxies. These bursts are often triggered by star quakes, violent shifts in the magnetar's crust caused by their own magnetic fields. For example, a gamma-ray burst from a magnetar in 2004 was so strong that it disrupted Earth's ionosphere. It hit Earth, and it was so intense that several satellites picked it up. The Swift satellite, built specifically to detect gamma-ray bursts from across the universe, didn't just detect the blast. It got hit with so much energy that its sensors got completely overloaded. And Swift wasn't even facing the burst. The energy was so strong it passed through the spacecraft and still overwhelmed its cameras. If a magnetar was located as close to Earth as the Moon, its magnetic field would erase all credit card data on the planet by wiping the magnetic stripes clean. Whoa, that's the level of power we're dealing with here. Magnetars are extremely active, but for a relatively short time. Their intense magnetic fields decay after about 10,000 years. After that, they stop emitting strong X-rays and gamma rays. Astronomers think that there are at least 30 million inactive magnetars in the Milky Way galaxy alone. These silent cosmic relics are scattered all over the galaxy. Neutron stars and magnetars serve as laboratories for extreme physics. They allow astronomers to have insights into the behavior of certain matter under conditions you can never replicate on Earth. The incredible density of these objects helps scientists figure out what happens when protons and electrons get compressed together to form neutrons. This creates states of matter that don't exist anywhere else in the universe. These violent explosions on neutron stars and magnetars also play a critical role in the formation of heavy elements like gold and platinum. These elements get scattered all over the universe during these energetic events, eventually becoming parts of planets and stars and you and me. Oh, by the way, NASA's NICER instrument has played the key role in uncovering the mysteries of neutron stars. Its ability to detect X-rays with high precision allowed astronomers to study the rapid spin of the neutron star we've been talking about and the thermonuclear bursts that occur on its surface. So, what could be nicer than that?
Locating the North Star is quite easy on a clear night. The only thing you need to do is find the Big Dipper. Those two stars on the end of the Dipper's cup point the way to the North Star. See? It's the tip of the handle of the Little Dipper, or the tail of the Little Bear. It's in the constellation Ursa Minor, over there. People have been watching the North Star for centuries. This bright star is also known as Polaris. It's situated almost directly over our planet's North Pole, which makes it a great landmark for a traveler without a compass, or a GPS on their smartphone. It's also Earth's closest Cepheid. That's what we call a star that pulses regularly in brightness and diameter. Polaris is also part of a binary system of two stars. It's got a dimmer sister. It's known as Polaris B. You can actually see it circling the North Stars from Earth. But the more astronomers watch Polaris, the less they understand. The problem is, no one can agree on how big or distant the star is. Scientists have several ways to estimate the mass, age, and distance of a star like Polaris. One method is called the stellar evolution method. After studying the brightness, color, and rate of pulsation of a star, experts use this data to figure out how big or bright it is, as well as what stage of life it's in. Once these details are clear, it's not hard to find out how far a star actually is. It's simple math once you know the luminosity of a star in real life and how dim it looks from our planet. Such models are especially precise for stars like Polaris because the rate of their pulsing is directly related to their brightness. This makes it easy to figure out the distance to any of those stars. Astronomers trust this method so much that Cepheids have become an important tool for measuring distances all across the universe. At the same time, there are other ways to study the North Star, and they don't agree with the stellar evolution models. Polaris is a so-called astrometric binary. It means you can see its companion going around it. It looks as if a circle is being drawn around the bigger star. To complete one orbit, the smaller star needs around 26 years. Even though astronomers haven't made detailed observations of Polaris B's full circuit, they've seen enough to know what its orbit looks like. Using this information, one can apply Newton's laws of gravity to calculate the masses of the two stars. Combined with the Hubble Space Telescope's new measurements, these calculations lead to very precise numbers. Polaris is supposed to be around 3.45 times the mass of the Sun. but that's much less than the mass you get from stellar evolution models. They suggest a value of almost 7 times the mass of the Sun. But there's another reason why this star system is weird. After calculating the ages of the stars, researchers concluded that Polaris b is much older than its bigger sibling, but it's extremely unusual for a binary system. Normally, both stars are of the same age. One explanation might be that at least one of the measurements is simply wrong. After all, Polaris is a difficult star to study. Since it's positioned above our planet's North Pole, it's outside the field of view of most telescopes. As for those telescopes that do have the needed equipment for measuring the star's properties precisely, they're typically used for studying much more distant and fainter stars. Polaris is simply too bright for such instruments. It blinds them. There's a theory that the main star of the Polaris system was once 2 stars, but they collided a few million years ago. Such a binary collision could rejuvenate stars by pulling in extra material and making the stars look as if they went through the fountain of youth. It would also explain some other oddities, since stars that appear as a result of binary collisions don't fit stellar evolution models. Unfortunately, so far, none of the theories have been confirmed. The North Star is actually a big deal. Earth is spinning non-stop, which causes the sun to rise and set and stars to travel across the sky. Our planet is also tilted. That's why we have seasons. If we drew a line through the axis Earth spins around and extended it over 300 light-years past the North Pole, at the end of that imaginary line, there would be the North Star. It stays almost exactly at the same spot in the sky at all times, and always points the way north. It's really important for navigation. People heavily relied on it in the days before GPS. If you were standing on the equator, Polaris would be right at the horizon. At the North Pole, it would seem to be right over your head. In other words, using the star's height in the sky, you can not only figure out the needed direction, but also understand where you are on Earth. Curiously, there's no South Star. There isn't a bright enough star right above the South Pole, but one day we might get such a star. When you spin a top on the table, its end moves in a circle. We know this phenomenon as precession. Earth behaves in the same way, and the North and South poles won't always point towards the same spots in the sky. In the next 26,000 years, it may cause the North Star to change from Polaris to a few other stars and back again. One day, the title of the North Star will go to Vega. It's the 5th brightest star in the night sky and the 2nd brightest in the northern celestial hemisphere. Vega has another name, Alpha Lyrae. That's because it's the main star of the Lyra constellation. Vega has been one of the most crucial stars to people since ancient times. It's very bright and blue, hence very recognizable. Vega was the North Star several thousand years ago, and it'll regain this status in 12,000 years or so. This star is located a mere 25 light-years from Earth. It's just 450 million years old, which makes it way younger than our own 4.6 billion-year-old star system. Astronomers study Vega to learn more about star systems in the early stages of their formation. Vega is almost directly overhead at mid-northern latitudes on a summer night. It hides behind the horizon for only 7 hours a day. You can see it on any night of the year. If you travel farther south, you'll find out that Vega lies below the horizon for longer periods of time. But in Alaska, northern Canada, and some parts of Europe, Vega never sets. Vega's blue-white light is bright enough to be featured a lot in ancient cultures, from the Chinese to the Polynesians to the Hindus. Vega's name can also be translated as falling or swooping. This is a reference to the times when people regarded this constellation as a swooping vulture, not a lyre. Vega was also the first star to get photographed, other than the Sun, of course. To do it, astronomers at Harvard College Observatory used a 15-inch refractor, and it happened again in 1850. Around 2 decades later, an amateur astronomer broke down Vega's light to reveal various elements making up the star. In 2006, thanks to telescopic observations, scientists found out that Vega was whipping around so fast that its poles were several thousand degrees warmer than its equator. The star rotates every 12.5 hours and is at 90% of its critical rotation speed. That's the velocity at which an object can tear itself apart. In 2013, researchers announced that they had discovered an asteroid belt around Vega. It means there might be planets somewhere out there among space rocks. There are two areas, an outer region that contains icy asteroids and an inner region with warmer space rocks. Scientists can examine bright stars like Vega using NASA's mission called TESS, which stands for Transiting Exoplanet Survey Satellite. It was launched in 2018 to conduct an all-sky survey. The main goal of this mission is to search for exoplanets, but the satellite can also look for star variability. By examining such stars as Vega, TESS can help scientists learn more about the early stages of star evolution. Most of those twinkling dots scattered across the night sky seem unreachable, but one of them is Beetlejuice, a star so enormous and nearby that you can see it with the naked eye. To find it, locate the first 3 big dots in the Orion's belt. A reddish star to the left is Beetlejuice. It's one of the brightest stars we can see from Earth, and it's just 640 light-years away. No big deal. Beetlejuice has a blue-white O-type star, which is one of the hottest types to exist. Beetlejuice was scorching hot, reaching temperatures of about 90,000 degrees Fahrenheit. Although that was back in the day, now it's an elderly star and it cooled down to just 5,800 degrees. You know, vacation weather. Blue-white stars are absolutely massive and burn incredibly bright because they have loads of hydrogen fuel. But they have a price to pay for this glory. They burn through their fuel super quickly. As they age, they transform into red giants. This is exactly what happened to Beetlejuice. It burned through its hydrogen and started burning helium instead. This caused its outer layers to puff up like a balloon, turning it into a red supergiant and making it one of the largest stars out there. Now it's stretching over 700 million miles in diameter. Now it's about 1,000 times bigger than our Sun. If Beetlejuice replaced it, it would swallow up Mercury, Venus, Earth, Mars, even Jupiter. And its atmosphere would almost reach Saturn. But something strange has been going on. Beetlejuice spinning way faster than it should for a star of its size. Huge stars like Beetlejuice are expected to rotate slowly, but it suddenly started spinning at a rate of about 3 miles per second. Thanks to powerful radio telescopes, Beetlejuice's orange-red surface can be seen in detail. That's how we learned that it often changes its brightness. Sometimes Beetlejuice shines super brightly and then gets very dim. This happens about every 400 days. And recently, a telescope called ALMA, which is made up of many antennas working together as one, showed that Beetlejuice's surface seems to be moving unevenly. It's like one side is coming towards us while the other is moving away. But all of it might be a trick of light. Beetlejuice isn't as smooth as our Sun. Instead, it's super chunky. Its surface is like a boiling cauldron. It's bubbling and churning incredibly fiercely. Imagine giant plumes of hot gas erupting from its core, reaching the surface and then vanishing back inside. And these bubbles are bigger not only than the Sun, but Earth's entire orbit around the Sun. These bubbles also rise and fall super quickly, even faster than a spacecraft. And maybe this tricks our telescopes into seeing it spin faster than it really does. Some astronomers also think that Beetlejuice could have swallowed up another star, and this gave it a spin boost. But these are all just theories. Things got even more complicated when Beetlejuice dimmed once again, this time in a pretty unexpected way. What's interesting, it was discovered using a weather satellite. A regular telescope had a hard time seeing Beetlejuice clearly because of Earth's atmosphere. So they used a satellite that normally watches Earth's weather, but can also take pictures of space. As we mentioned, it usually brightens and dims about every 400 days. But recently, it suddenly dimmed by 2.5 times more than ever before. This event got the name the Great Dimming. The first theory said that Beetlejuice cooled down and sneezed out a bunch of material, creating a massive dust cloud. This cloud blocked the view of the star, making it look much fainter than usual. They also noticed something strange happening to that dust. It started behaving differently, which might be a sign that something deep inside the star was causing trouble. Beetlejuice's brightening and dimming cycle now happens faster in just 200 days instead of 400. And to add to the mystery, in the spring of 2023, it started shining even brighter than it normally does at its peak. Why is this frightening? Because Beetlejuice might be preparing for its grand finale, and this wouldn't be very good for Earth. We might be on the verge of a supernova. When massive stars like Beetlejuice run out of fuel in their cores, they start burning different elements like carbon, oxygen, and silicon. Eventually, they end up with iron in their cores. At that moment, everything changes. Adding helium to iron doesn't produce energy like other reactions do. Instead, it sucks up energy. This causes the star's core to collapse, leading to what's called a core collapse supernova. A spectacular, breathtaking show. Supernovas are so bright that they can outshine entire galaxies. But a Beetlejuice supernova would be special. Because it's relatively close to us, it would be so bright that we could see it even during the day. When it happens, Beetlejuice will shine as brightly as a full moon, but all that light will be concentrated in one point. For about 2 months, it will be so bright that you could read a book just from the light of the supernova, even if you turned off all the city lights and had a clear sky. The idea of witnessing Beetlejuice explode as a supernova is truly thrilling. After all, the last time a star went supernova in our galaxy was way back in the time of Johannes Kepler, more than 4 centuries ago. That event, known as the SN 1604 or Kepler supernova, dazzled the sky for weeks. But don't get too excited yet. We're not sure when exactly it'll happen. One study says that the star might be in its carbon-burning phase. If we're near the end of that stage, then Beetlejuice might blow up very soon, during the next tens of years. But it's nearly impossible to determine because during that last phase, the star barely changes at all. Even though Beetlejuice is close enough for us to study its surface, we can't peek inside its core to see what's really happening with it. We might as well be at the beginning of the carbon-burning phase, and in that case, we might have to wait 1,000 more years before that cool supernova. Another study says that Beetlejuice might have less than 300 years of fuel left in its core. They say that Beetlejuice is known to expand and contract regularly, and its pulsation pattern hints that Beetlejuice is much larger than we previously thought. This would suggest that the star is further along in its life cycle and closer to going supernova. Other guesses come from observations of similar stars. For example, a star called VYCMA in our galaxy is thought to be closer to going supernova than Beetlejuice, and it's been dimming steadily over the past century, unlike the relatively stable Beetlejuice. If Beetlejuice was about to go supernova, it would dim steadily and very quickly. Also, historical records suggest that about 2,000 years ago, people saw Beetlejuice as yellow, not red. If that's the case, then we might be in its early last days after all. In other words, we have no idea whether it will go supernova tomorrow or in 1,000 years. We just gotta wait and see. But let's say it goes supernova tomorrow. What happens to us then? The 1987 supernova in the Large Magellanic Cloud showed that the effects from the supernova might be so strong we can sense it even from very far distances. The Large Magellanic Cloud is almost 170,000 light-years away, and we still detected the radiation. It's kinda hard to say exactly what the danger zone is. A rough estimate could be around 100 light-years. Luckily, Beetlejuice won't pose any danger to humans. It's hundreds of light-years away, and its supernova won't influence us in any way. We'll be able to enjoy its supernova beauty without any harm.
Scientists were looking at a list of gas clouds when they saw something strange. 5 groups of blue stars that are not quite a galaxy and not a known type of star cluster either. These groups of stars are called blue blobs, and they're located in the Virgo galaxy cluster. Now, the big question is, how did these blue blobs form if they don't have any nearby parent galaxy where they could form? Scientists realize there are some heavy metals present in these blobs. Generally, when stars are born, they create heavy elements called metals. These metals are essential building blocks for new stars. In big galaxies, many stars form over time, and as a result, more metals get created too. These heavy metals in the blue blobs were a clue that the stars in these blobs were formed from gas that was stripped from a larger galaxy. Think of it as a piñata. The candy is the gas, and the piñata is this bigger galaxy. The blue blobs are the leftover candy that was scattered around. Wow. Didn't expect to get hungry while talking about stars. How did the gas get stripped away from the bigger galaxy anyway? There are 2 ways. When galaxies pass by each other, their gravitational attraction can cause gas to be pulled away from one galaxy and into the other. This is called tidal stripping, and it's the first way these blobs can happen. It's like when 2 magnets attract and pull metal objects toward each other. Another way is ram pressure. This happens when a galaxy moves through a cluster of hot gas at a pretty high speed. The gas in the cluster can push against the gas in the galaxy and force it out back, similar to a car pushing air out of the way as it drives, and you lose your hat in a strong wind. As time goes by, these stars in the blue blobs will keep on moving apart. Eventually, they will form smaller clusters. Have you ever seen pictures of Earth taken from space? They're amazing. But have you seen the one with 2 blue blobs of light? The first blob of light you see here is a large lightning strike in the Gulf of Thailand. It's rare to see lightning from space because of all the clouds, but this one was so huge it lit up the clouds around it like some kind of a brilliant ring. How cool is that? The second blue blob of light is a bit different. We're looking at the reflection of the moon's light on our home planet. The moon actually reflects the light coming from the sun onto the Earth. And when that light goes through the Earth's atmosphere, it creates a big blue blob with a fuzzy outline. It's like a shiny blue hat our planet is wearing. It's similar to the reason why the sky is blue during the day. When sunlight enters Earth's atmosphere, gases and particles in the air scatter it in all directions. Blue light has the shortest and smallest waves, so it gets scattered the most. And that's why we get to enjoy a beautiful view of a clear blue sky. The same thing actually happens to the light coming from the moon. When it reflects off the Earth and goes through the atmosphere, the blue light waves get scattered the most, making the moon appear blue in the photo. Speaking of unusual stars, there's one in the Centaurus constellation called Lucy. It looks like a tiny white dwarf, but it's actually very dense. There's a mass of the entire sun squeezed into an object only 1/3 of the size of our home planet. That's like stuffing a whole watermelon into a golf ball. Lucy is also incredibly cool. Its core temperature is almost 12,000 degrees Fahrenheit. This may sound hot at first, but for comparison, our sun is about 27 million degrees Fahrenheit. And the best part that makes Lucy so special is the diamond at its heart. Its carbon core has crystallized into a massive diamond that's 10 billion trillion carats in size. It's hard to even imagine how big it is. Scientists found out about this awesome diamond by listening to the star's vibrations, which is like a star's heartbeat. And after they discovered Lucy, scientists found some other stars with crystallized cores and massive diamonds the size of Earth, too. Our universe is like a giant jewelry store. Most of the astronomers from the northern hemisphere are familiar with the star named Vega. First, it's brighter than expected. But if you could take a look at it from a different angle, you'd see this star is actually squashed. It has a specific oblong shape because it rotates at a high rate. It spins once every 12.5 hours, which throws the material out around its equator. This material then cools and darkens, and forms a dark, mysterious halo around Vega. When stars reach the end of their lives, they often explode in a dazzling supernova, getting brighter and brighter before they finally fade away. But one supernova, IPF-14Ls, decided not to obey the rules. It started to fade away like most other stars, but then, when everyone expected it to be gone, it suddenly came back to life and brightened up again. And not just once. It kept fading and brightening at least 5 times in a row. Scientists were so surprised to see this. When they measured the light from the supernova, they found it was evolving 10 times slower than other stars. It was aging way more slowly, too. When it looked 60 days old, it was actually 600 days old. It could be even older, because scientists had recorded another supernova in the same spot almost 70 years ago. There are some theories as to how it could have happened. Maybe the supernova was bumping into some surrounding material and then making it glow. Or maybe it was a giant star that was shedding material all the time to prevent, or at least postpone, its own collapse. At first, it may seem like you're looking at a simple variable star here, my Camelopardalis. But when astronomers looked more closely, they realized it was a pair of stars. The two stars are moving around each other at really high speeds, and their atmospheres are starting to mix because they are so close. People believe this example is the start of a union between two stars. In the end, the two celestial bodies, which already weigh 32 and 38 solar masses each, will join together to make a gigantic one with more than 60 solar masses. Scientists have thought for a long time that this is how super big stars form. They've never really seen it happen. The universe is 13.8 billion years old, and from what we can see, one mysterious star, HD 1140283, could be 14.4 billion years old. Something's not right here. This star has all the chemical signs of a second-generation star, which is a star that formed from gas and dust after the first generation of stars exploded. This star, sometimes called Methuselah's star, is 190 light-years away. Its brightness, distance, and composition help us figure out how old it is, at least 13.2 billion years old, while the age of 14.4 billion years is probably put there as a potential range. Even if it's younger than the universe, or is it? It's still by far the oldest star near us. Let's not forget the one with a tail either. It's called Mira. Sometimes it's bright, and other times it's faint, making it a bit of a tricky one to spot in its constellation. Sometimes it's one of the brightest stars up there, while other times it is one of the fainter ones in its constellation. It's the system with two stars, a red giant and a white dwarf. The red giant used to be like our own sun, but now, as it's closer to its end, it's shedding its outer layers into space. And Mira has a comet-like tail too. As the red giant sheds its outer layers, it creates a stream of gas and dust that follows the stars as they move through space.
Imagine a being so powerful it can suck in entire galaxies, so mysterious it's invisible to the naked eye, and so impressive it bends the very fabric of space and time to its will. Yes, meet my mother. Just kidding. Actually, meet the ultimate superhero of the universe, the black hole star. What is it, and how does it work? Well, let's find out. The universe is full of marvels, and the black hole star is one of the most impressive ones. It's a supermassive force that can bend the laws of physics, and a true enigma for scientists to unravel. No wonder science fiction writers find them so captivating. A black hole star, also known as a quasi-star, is a hypothetical type of extremely massive and luminous star that may have existed early in the history of the galaxy. They're predicted to be as luminous as a small galaxy, but unlike modern stars, they weren't powered by nuclear fusion in their cores. A quasi-star's energy would come from material falling into a black hole at its core. And yes, just like a normal black hole, these stars have the power to suck in anything and everything that gets too close, including stars, dust, and even entire galaxies. But how is it possible that the star is born from a black hole? And what's more, how do they continue to coexist together? Well, first let's discuss how black holes are born in general. It all starts with a supermassive star, one that is at least a few times more massive than our own Sun. This giant of a star burns bright and hot, shining with the light of 1,000,000 suns. But eventually, it runs out of fuel and its fate is sealed. As its lifespan comes to an end, it makes one final massive boom, a blast so powerful it can outshine an entire galaxy. This blast is called supernova. During this boom, the outer layers of the star fly away, while the core gets squished together by its own gravity. If the squished core is heavy enough, it can keep squishing until it becomes a black hole. And just like that, a black hole is born. Don't even try to put diapers on this thing. Now, this cosmic monster baby can continue to grow by swallowing up anything that comes too close, including stars, dust, and even entire galaxies. This is basically what's happening now in our universe with supermassive stars. But what about quasi-stars? The formation of a quasi-star could only happen early in the development of the universe, before hydrogen and helium were contaminated by heavier elements. And because of that, quasi-stars have one important feature. They are gigantic, so enormous that it's literally impossible to imagine. They may have been dwarfing even the largest known modern stars, like VY Canis Majoris and Stephenson 218. No wonder they're so scary. They were born from protostars, one of the first stars in the universe, the great-great-grandfathers of, everything. So now imagine a protostar so massive that its core collapses into a black hole, just like we described before. But the key difference is that in a regular supernova, the outer layers of the star are blown away by the energy released during the boom. Meanwhile, in a quasi-star, these outer layers are massive enough to absorb the energy without being blown away. What do we get in the end? A star with a black hole in its core that weighs from 1,000 to 10,000 solar masses. This quasi-star is about 14,000 times bigger than our Sun, which makes them bigger than any star we know today. These celestial titans have some pretty crazy properties. Once a black hole is formed at the center of a giant protostar, it starts to give off a ton of energy. This energy helps to balance out the force of gravity, making it kind of a giant fusion-based star. They would be so bright that each one would look like a small galaxy. Quasi-stars would have a pretty short lifespan, around 7 million years. Just for comparison, our Sun is about 4.5 billion years old, and it's only halfway through its lifetime. But either way, during this short period, the black hole at the center would grow to be about 1,000 to 10,000 times the size of our Sun. Quasi-stars are also thought to be super hot, with temperatures reaching over 17,500 degrees. But as a quasi-star gets older, it starts to cool down, and its outer layers become see-through. Eventually, it cools down to a temperature of 6,740 degrees, and at that point, it's curtains for the quasi-star. It can't survive at that temperature, so it just dissipates, leaving behind an intermediate mass black hole. Unfortunately, right now, there's no observational evidence for the existence of quasi-stars. This is because they're thought to have only existed a very, very long time ago. They may have been very massive population 3 stars, which are extremely rare and difficult to detect. It's also very unlikely that any of them would still exist today because of their super short lifespan, only 7 million years. So why do scientists believe that quasi-stars could have existed? Because they're looking for ways to explain how supermassive black holes formed so early in the history of the universe. They're found at the center of most galaxies. But how could these monsters have formed so quickly? After all, it takes a really long time for small black holes to grow into supermassive ones. This is where the idea of quasi-stars come in. These stars aren't just destructive forces of nature. They're like the black belts in the martial art of gravity. They can bend and twist anything to its will. That's why these stars, if they really existed, had to play a crucial role in the evolution of galaxies. They must have been instrumental in shaping the universe as we know it. So, those intermediate-sized black holes that they left behind could eventually turn into supermassive black holes in the center of galaxies. But we're still yet to solve this cosmic mystery. Detection and study of black hole stars is like trying to find a needle in a haystack. Only instead of a needle, it's an invisible and mysterious object. And instead of a haystack, it's the vast expanse of space. But with the help of some pretty cool technology and a lot of brainpower, scientists are getting closer to uncovering the secrets of these celestial giants. Here are some things that can help us in this research. First of all, gravitational waves. They're like ripples in the fabric of space-time, caused by the movement of massive objects. Albert Einstein predicted them way back in the 20th century, but they were finally detected only in 2015. We caught them by observing the collision of two black holes. This discovery confirmed that black holes can merge and that they're a powerful source of gravitational waves. Scientists think that by studying these waves, they can learn more about how black holes form and grow. We can also try to detect quasi-stars by observing the effects of their gravity on nearby objects. It's like trying to spot a criminal by their fingerprints. For example, if a black hole is located near a star, scientists can observe the star's light being distorted as it's pulled toward the black hole. And of course, we can use our technologies, such as X-ray, infrared, and radio telescopes. This allows us to study black holes in various ways and at different stages of their lives. In other words, scientists are working hard to uncover the secrets of these celestial giants. We develop new telescopes, search for primordial black holes, and try to understand the connection between black hole stars and dark matter. And we're making some pretty incredible discoveries, just like with gravitational waves. All these things will bring us closer to uncovering the secrets of quasi-stars. And when we find out the truth about them, it will become a new page in our scientific history.